वो हटाते तो उसमें बाकी चीज लग जाती है।
अच्छा रहने दीजिए, फिर उसको मैं मीटिंग के बाद में भेजता हूँ ड्राफ्ट है मेरा। तो
सर जी नमस्कार 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 अंशुल सर।
हाँ वो मैं क्या कि मेरी आवाज आ रही है नहीं वो
ऑडिबल आवाज आ रही है। Good morning, everyone. For today's session, I would like to invite Dr. Manisha Gupta ma'am to introduce Professor Manvin. Sorry, Mandalvi sir. All esteemed guests present here. I, Manisha Gupta, Assistant Professor Physics, Government Science College, Raipur. It's my privilege to introduce Professor Anshuman Dalvi from Department of Physics, BITS Pilani, Rajasthan, for the technical session 2. Mr. Dalvi completed his graduation from Government Holkar Science College, Indore. The master's degree from School of Physics, DA University, Indore. After that, he has completed PhD from IIT Kanpur. His field of interest are in energy materials and storage devices, lithium and sodium ion batteries, supercapacitors, electrical transport, and condensed matter experimental physics. He has 40 international publications in his name, of which 10 are most recent, most impact index international journal publication. Now, I invite Professor Dalvi to conduct the technical session 2.
I think I'll require permission to share my screen, right?
Yes, sir, you are co-host.
You can share your screen.
Sir, you can share your screen.
Yeah, but I'm unable to do it because here host disabled participant screen sharing. So, what to do? How to do it? Yeah, now I can do it. Very nice. Just a minute, huh? Share. So is it visible?
Yes, Mr. Lalit.
So there will be some delay. How it works. Let's see. All right. So.
But sound is.
What is that, sir?
Yes, sound is a little bit low.
Low, is it?
I think maybe because of the distance.
Possibly, no.
Mic and.
So is it fine if I speak now this way? Because at this point of time, this is the only possibility with me. Because, yeah. So should I start speaking?
Yes, sir.
Yeah, fine. So anyway, if it is little low, then also I'll be able to speak and I'll be able to tell you that what I do here and how the things move. All right. So the topic I have kept is at little research level because this is a workshop, and this workshop, as Mohanji has designed, and Professor Gupta and other people from outside country are also participating. Other participants are also there. And I believe that most of them are oriented towards research. So I have planned to introduce to you people, not really on very fundamentals, but little applied part of my research. I'll not talk about much of the basics here, but I'll give you some idea about the research work which is in which I'm engaged in at present in BITS Pilani. So this is my research group here in Pilani, and you can see that most of them are girls and only 2 boys who have contributed so far. And these are the list of publications in last few years in our lab. The topic I have kept is on solid state supercapacitors. Supercapacitors are already there in the market, and people are working on these application of supercapacitors in electric vehicles. They are working on various types of possible usage in other devices also, making their combination with batteries and making some kind of hybrid devices so that we can look for a very proper energy storage system in this country, in this world. And the most important objective is the energy storage using combination of these batteries and supercapacitors. That is what we are going to look into this one. Most of the devices so far which are there in the market are liquid based, as all we know. So all the lithium batteries, the upcoming sodium ion batteries, everywhere the liquid electrolyte is being used. But liquids have some drawbacks, and therefore we have to look for substitution of liquid with some kind of solids, some solid materials, so that we can achieve high temperature stability, we can achieve the low dimensional stability as well. Because of various requirements of the electronic devices, we have to go for the low dimensional systems also. Therefore, solid state and solid state ionics, and therefore role of physicist comes into the picture. Professor Verma, he is doing excellent work in Bhilai, and I have visited his lab 2 years back, just before the lockdown, and we were very happy to see that in limited resources, what beautiful work can be done. And so many people are being trained there in the theoretical aspects of the solid state ionics. I'm very happy to share our work, which is also, we started with limited resources, but now we have sufficient things, sufficient funds to do some kind of cutting edge research work. All right. So is the slide visible? I'm on the outline slide. Is it visible?
Visible, sir.
Yes, thank you. Yeah, so here, the efforts from 1960s are to replace the liquid electrolyte of the batteries and other energy storage devices by the solids. And what is the advantage? Advantage is that you will be able to get, wide voltage stability. You will be able to get rid of the corrosion kind of things. You will be able to increase the shelf life. You will be able to realize what you say, low dimensional device, micro batteries, nano batteries, because your VLSI designs nowadays 10 to the power 9 number of transistors on 1 inch square of area. If such kind of devices are coming up, then the energy support to that device should also be of the similar dimensions. So low dimension is very important thing, and the high temperature application. The liquid electrolytes which are being used in the devices are liquid based. I mean, they are not thermally stable. So if you go to lower temperatures, they freeze. If you go to higher temperature, they evaporate or decompose. So batteries will be spoiled. Therefore, solid state. So I'll talk about the solid state. I'll talk about the issues which are related to solid state. And then I'll come back quickly to the supercapacitors and the work which we do here in Pilani. And of course, in the limited resources, but whatever we do in Pilani is something which can be done in India also, in other labs also. So it is, an idea is to inspire people to work in this interesting field of research, where there are many vertices, many interesting dimensions which can be achieved, and many interesting success stories can be written in the near future. So that with that idea, let us begin with the understanding of ionic transport in solids. So when you say a solid, then all this condensed matter physics, the solid state physics, Kittel based course, in the very first chapter, we talk about ionic solids being zinc sulfide, cesium chloride, sodium chloride. All these have, if you go, the most favorable, most comfortable is the sodium chloride, the salt, which is there in our table also. Sodium chloride has a FCC structure, huge packing, 74% of the volume is occupied, then the ionic transport is difficult. When people, developed in last 40, 50 years, various interesting structures inside the solid, so that ionic transport can be made via some tunnel-like structures. And we have such tunnel-like structures possible, using which we can achieve very fast ionic solid. And the ionic solid can be comparable nowadays to molten salts and aqueous solutions. So as far as in-grain conductivity is concerned, then you have nasicons, garnets, and various other perovskites kind of materials where the conductivity is extremely high, comparable to aqueous solutions, molten salts. But then it is about the grain boundary. So again, the solid-solid interface. One of the grain and another grain, when they are in contact, then they exhibit a poor conductivity. The ion, as long as it moves inside a grain, it is very comfortable to perform high conductivity, to give high conductivity. So bulk conductivity of these developed ionic compounds is very high. But when you go and cross the interface, you lose the conductivity because of the high grain boundary impedance. And that is the biggest problem for the application of ionic solids in the real energy devices. Because if you have large grain boundary impedance, then there is an issue, we cannot achieve high conductivity. The another issue is the interface, the electrode-electrolyte interface. So even if we know what is P, how we make PN junction, then it is not that we have a P and we have an N and we join them and make a junction, not that way. PN junction essentially is in one semiconductor single crystal. One side you grow the N type of impurity using diffusion, the other side using P, and then you talk about PN junction. Now that is the PN junction where again there is a potential barrier and all those things come. But here we talk about two solids coming to each other, making an interface, and through that interface we expect a fast ionic transport without any potential barrier. So there is a challenge. So you have a challenge of wettability, huge energy barrier, poor junction, poor the sense that you cannot utilize the complete surface area. Both the surfaces have their own natural roughness, and there is a problem. Then there is another issue, the thermal expansion. Thermal expansion coefficient, if suppose you want to go high temperature, then different materials will have different thermal expansion coefficients, and one of the material will expand more, another one will be expanding less, and that also is a reason for the poor electrode-electrolyte interface. Because of various reasons, the energy inside the solid electrolyte, inside the electrolyte may increase, and those things may cause a poor interface again. So interface is one of the important things on which all the people, solid-state ionics people, the people who want to use the electrolytes, solid electrolytes for the batteries, are working actually. Okay. One of the interesting material is nasicon, sodium superionic conductor, which was discovery in late 70s discovery is nasicon. But then what is this structure? Here we talk about. Hello. Am I audible, Mohanji? This is fine. मेरी आवाज आ रही है आपको?
Yes, sir. Yes, sir.
ठीक. All right. So you talk about such kind of skeletons which should be prepared. For example, this titanium octahedral and phosphate tetrahedral, when they are made, when they are joining the corners, then there is a lot of free space inside. And this is a three-dimensional tunnel-like structure. And now it is possible to think about such a three-dimensional tunnel-like structure in lithium systems also. In garnets also a very similar thing happens whenever the tetrahedra, octahedra share the corner rather than sharing the surfaces, the faces. Then we see that we are able to achieve space inside the solid, and using that space, ionic transport is possible. three-dimensionally it is possible. So this is one of the important material, and this material is a competitor, if you see, for the future batteries. What will happen after 1930s? People are predicting that it will be a century for solid-state ionics. And one of the competitor will be garnet, another will be the Nasikon, and third one will be the perovskite. That is what people talk about. There will be other challenging new materials which will come up in future. All right. So another competitor, or one of the most important choice, you can say, where a solid-solid interface can be established is polymer. A lot of work on solid polymer electrolyte has been done by Professor Ravindra Gupta ji and of course Verma ji and Professor Agrawal's group there. And solid polymer electrolyte still is one of the fascinating material for the ionics community. And what happens in solid polymer electrolyte is, and why it is an important choice, is because if you take about two contacts of the solids, then polymer is the best choice to have a smooth contact at the interface. Polymer ka jo solid ke saath contact hai, that can be the easiest and smoothest contacts as far as the solids are concerned. I'm not talking about the gel at the moment, only solid polymer electrolyte, which will be liquid free. What happens here? You have a polymer, then there are certain amorphous regions in the polymer. If you keep on adding salt, then these amorphous regions increase. Either their number will increase or their volume will increase, and there will be a connectivity in the amorphous regions. And finally, the ion chain coupling mechanism leads to the ionic transport here. So lithium ions or sodium ion based polymers are there, but the conductivity is limited because of the coupling mechanism. Lithium ion has to couple with the chains, and this coupling doesn't provide a fast ionic transport. So you have to break the coupling and do some kind of engineering inside this material so that these lithium ions can be freely moving like tunnels inside the polymer, and the polymer will be able to provide a good interface. So now I think I lost the connection, is it? Am I there now again?
Yes, connected.
कुछ तो भी हो गया, एकदम नेट चला गया था. Right. So now you have new materials where inside the ceramic particles can also support the ionic transport, either by polymer ceramic interface or by providing pathways through their own grains also. Now a lot of mechanism people are thinking about that, how the ionic transport is happening, whether through the grains of the ceramics or through the interface of the polymer ceramic. You can put polymer in ceramic, you can put ceramic in polymer and make a huge compositional variation range now. And now since they are developed, then the conductivity has reached to a very high value. And this high value of conductivity is about 10 to the power -4 in sodium as well as lithium systems. So we can think about preparing a proper or using them in various types of devices now. So that is the interesting thing on which we have been working, that we are taking the polymer and making their compositions with these Nasikons, and taking the Nasikons and their compositions. Meeting चल रही है, बाद में बात करेंगे. Taking the Nasikons and making their composition with ionic liquids also. This is also a very interesting way of enhancing the conductivity by using some small amount of little amount of ionic liquid. All these kinds of things are giving us interesting electrolytes nowadays, where we can see the role of electrolyte in the performance of the device. All right. Now I come back to the real point. The supercapacitors. So supercapacitors are the materials, are the devices which are considered something which is going to complement the batteries in the future. In the present also it is happening, very nicely happening. Supercapacitors means they are the fast charging discharging devices. They can deliver huge amount of power in a very small amount of time. Because normally the supercapacitors will have a smaller area, smaller discharge time. So you are not limited to the chemical reactions which are happening in the batteries. Supercapacitors are using this electrostatic phenomena of the charge storage, which we have seen in our capacitors and capacitors. Same thing we are just applying here and apply using the nanotechnology to make some kind of supercapacitors, some kind of capacitors which are treated or which are called supercapacitors. So let us talk about supercapacitor a little bit. So first of all, supercapacitor is not to compete with the battery, but it is to complement the battery. So if for an ordinary person, ordinary means ordinary in the sense that a new person in this field, a new learner, battery is like a marathon runner, because battery can provide a can store a huge amount of energy, and that energy can be delivered for a very long time, because the outcome of the energy is dictated by the chemical reaction of the battery. Chemical reaction will have a time constant, that much time it will take and it will deliver. Will have Nandita Tamrakar ji, आप mute कर लें तो अच्छा रहेगा. Yes, thank you. So here we have supercapacitors, which we talk like a marathon, which will talk like a 100-meter runner. इसको बोलते हैं sprinter, like Usain Bolt. So he can deliver his complete energy in 10 seconds, less than 10 seconds, and super performance. So the way Usain Bolt runs, you can say, is like delivering huge current from a device, and the way Kipchoge runs is like a 42 kilometers run, slow running, but a steady running, and it is useful at small amount of current for a very large time. So supercapacitor means large amount of current in a very small time. Battery means a steady and small current for long time. Both have their importances, but there are places where you need large current in small time. For example, a vehicle, when it is climbing an incline, then you have to accelerate. If it is not having any other source, then you have only battery. Battery can provide only a stable voltage outcome, current outcome. So there you use supercapacitor. Suddenly huge amount of current it can supply, and then you can climb the inclined plane, the pull or whatever. And here we talk about the Ragon plot, where when we compare specific energy and specific power. So energy means you see how much you can deliver, but you can deliver in large amounts of times. And power means instant. Power means it's about current, or energy divided by time is power. So you have to see that you deliver it for a very long time. Then you talk about energy, and when you want to deliver energy in a very small time, then you talk about power. The ideal situation would be devices which will have high specific energy and high specific power, and that is what the interest of the scientific community. But when you talk about energy, then that is higher for batteries, and batteries will have smaller power outcome. And when you talk about supercapacitors, then supercapacitor has very large power outcome, but very small energy they can have. So therefore, they both of them are important, and their combinations in the future are going to dictate the direction of the energy devices in the future. And it is an open field in which now many people are working in India and in abroad also. This is a simple slide on supercapacitors. You talk about double layer supercapacitor, then hybrids, then pseudo capacitors. Pseudo capacitors will have some kind of surface chemical reactions also, and electric double layers will have a pure electrostatic phenomena of energy storage. I'll talk about today's lecture. In today's lecture, the work on electric double layer only. All right. What happens in a normal capacitor? You have capacitor capacity is given by epsilon 0 A upon D. Now, how to increase the capacity? By either by increasing the area. If you increase the area, then you can increase the capacity, or you can decrease the separation between the plates, then you can increase the capacity, or you can introduce some kind of dielectric material inside the capacitor, where the dielectric will reduce the potential, therefore it will enhance the capacity. All right. So these are the 2-3 methods by which normal capacitors work. And if you can see, overall, from the positive to negative potential, there is a gradual fall of the potential, positive plate to the negative plate. And you say gradient of this one is the potential is the electric field. Electric lines of forces are parallel everywhere. You know, sigma upon epsilon 0 is the electric field there. And the energy is stored in the electric field here. Now, as I said, you have a limitation. You cannot make capacitors of the size of your home because area you have to increase. You cannot decrease the distance also to a very significant, because there will be an issue corresponding to how close the two battery plates can come. You have to do now a new business which is called the nanotechnology. You have to look for those materials which are nanomaterials, which can be introduced or which can be there at the interface and play the role of larger surface area. At the same time, the interface can be decreased by, again, the concept of electric double layer. So I'll show you what is that double layer. This is the supercapacitor, a typical supercapacitor. And here what happens is, in between, instead of a dielectric, you have a liquid electrolyte. I am getting some disturbance. Someone is speaking, so can you mute, please? Yes. So in between the two plates, you have liquid electrolyte. All right. And now you give a potential. So one plate will become positive and another plate will become negative. What happens? Liquid will have some kind of molecules, neutral molecules. Those species will come, and right now, at the very first instant, they will come and get adsorbed on the surface. This adsorption is a chemical phenomenon. It's a chemical requirement of the electrode to have some kind of adsorbed molecule. So on the adsorbed molecule, now the moving charges will come. The electrostatic requirement has to be fulfilled. So first requirement is the adsorption. Second requirement is the electrostatic interaction. So these are the mobile charges, the ones in the center. They will come and they will form two capacitors at the interface. So one capacitor is near the positive plate. Another capacitor is near the negative plate. And you have ensured that the surface area is very high, for example, 1000 meters per gram. For example, 1000 meters per gram. And you see that this kind of surface area doesn't require real big space, but at the nano level, you are able to generate that surface area. Now we bring them, then what is the model? You have two capacitors on both the sides, and sometimes you can talk about some small resistance in between. The normal capacitor will have a insulating material in between, and here you will have a conducting liquid in between. So that is a supercapacitor which comes. Now this is purely because of the electrostatic interaction. So if the electrostatic interaction is there, then the charges are being pulled from the liquid, and they are there at the interface. When you discharge, then whole charges now will be going back, because surface area is large. So large number of charges are able to accumulate there. And if that is the thing, then because there is no chemical reaction involved, soon you will be able to discharge or take out all the charges in no time, in quick time. So the voltage profile is like huge potential drop at the interface in the double layer. These are also called sometimes the Helmholtz double layers. And in between, there is almost no potential drop. So though there is no electric field also in between. So everything is happening sharply at the interface. A large potential drop at the interface leads to a huge electric field also at the interface. And finally, what happens is only interfacial phenomena remains. In between, only job of the electrolyte is to provide the ions whenever they are required. So they are going by the diffusive mechanism and coming back to the electrolyte by diffusion mechanism. And as such, there is nothing else is happening. So electrolyte's role is to provide free ions, and how fast the electrolyte can provide the ions depends upon the conductivity of the electrolyte. So far, this is happening using a typical liquid electrolyte. And now, for last 4-5 years, people have been trying for solid electrolytes and they are used in supercapacitors. I'm talking about that now after some time. So this is kind of adsorption phenomena. When you talk about Helmholtz layer, the first layer is of the inert molecules. The second layer is the solvated ions, and these solvated ions are actually the charges, free charges, mobile ions in the liquid. And this double layer, so double layer doesn't mean both side layers. Double layer means on one side you have 2 layers, on another side you have 2 layers. So in a one capacitor, you have 2 capacitors at the interface. So because you have 2 interfaces, so 2 capacitors are there. So that is the real model of your super capacitor. Requirement is huge surface area. So you have to go for 1000 to 2000 meters square per gram kind of surface area. This is already I have discussed. And you have to create the interface very properly. If you are able to create the interface, then you are able to really get a very high capacity. And when the capacity is very high, then you will be able to discharge huge amount of current in very small time. So, batteries are charged and discharged very slowly because they'll need time to charge. They'll need time to complete discharge. But super capacitors can be, charged very fast. In few seconds, it can be charged to a full loading and it can be discharged also to a full loading. And this process, if you do it very high currents, then, we can draw huge currents in no time. That is the beauty of the supercapacitor. So this is the idea that you have to use this kind of high surface area material. Activated material. Activated materials means it has large surface area and the surface is active to take some part somewhere for the chemical reactions or for the adsorption process. So that is what we say activated carbon. Now this activated carbon nowadays available everywhere. At least 1000 meters square per gram activated carbon you can get in your that semi-permeable membrane-based AquaGuard drinking water machine, right? So that is also available cheaply nowadays. But if you want to go for more high surface area, it is little costly. All right. So now the thing is we have to go for liquid-free supercapacitors. That is the idea because it is in parallel to the liquid-free solid-state batteries. Liquid-free batteries. So you are looking for solid electrolytes for the batteries. So we are also looking for solid electrolyte for the supercapacitors. So there is a huge advantage, as I have mentioned, for something which is liquid-free, and therefore we would like to go for solid-state devices. In parallel to solid-state batteries, we talk about solid-state supercapacitors. Quote unquote, we say all solid-state supercapacitors. All solid-state means no liquid at all. There should not be any role for liquid inside, only solid interface, solid electrolyte, and solid, solid electrodes also. And therefore, there is a huge possibility for people like physicists like me and our other colleagues here. They can contribute because we understand chemistry little, at a little lower level, but we understand physics well, that where to apply physics, what is happening, how to understand the mechanisms. There we can contribute very nicely. And if less chemistry is there, then we can certainly go for a very good understanding of the future devices also. You can predict that what best we can do out of these ones using computational techniques, as Professor Verma is doing, and using the sophisticated experimental techniques, and with continuous exchange between theoreticians and experimentalists, we can design new things. Now I will tell you in next 25 minutes story of my work, what we do here. So we are talking about, some kind of, as I introduced, that we are developing initially for last 10 years, we were actually developing polymer ionic conductors where ceramics are added in the polymer. Ceramic means the ion conducting materials are added to the polymer. And if they are added to the polymer, being a physicist, I was studying very systematically that what are the electrical transport possibilities, what is the mechanism. So using various techniques like X-ray, absorption spectroscopy, and high temperature X-ray, and many other things we used, and using conductivity structure correlation, we tried to understand the mechanism of electrical transport in those materials. And later on, after getting the understanding of mechanism, when we found that the conductivity can be enhanced to a much larger extent, for example, 10 to the power -3 to -4, then such materials can be used for devices also. So on the one side, we were trying for batteries. On the other hand, we were trying for the supercapacitors. And at the moment, my focus is on supercapacitors because it is, it gives quick results actually. Batteries require a lot of huge investment, and that much money in India, no researcher can claim to have consistently. That is very important. You can get one project, but nobody knows you'll get another project or not. It's a huge competition. So you should do whatever consistently you can do in limited resources you can do. So what you do is that here we also develop activated carbon. So activated carbon we coat on graphite using some simple Dr. Blade technique. And using that, when the graphite is coated with activated carbon, simple job, you put your polymer film in between. And this technique we developed that do a lamination, hot roll lamination. So when you do lamination, then instantly the lamination layers will be going above the melting point, and then they will be cooled also. So when the melting point is more, the material goes little above the melting point, then the interface is established smoothly. That idea we started with this solid state supercapacitors, where a solid polymer electrolyte film was used, and it was in between activated carbon graphite, which is coated with activated carbon. And now, of course, we are working on pseudo also. But today's job is to tell you that what are the things which we have done. All right, in supercapacitor, these are the basic fundamental characterization parameters which people talk about. So one is the capacitance. In battery, we talk about capacity, but here we talk about capacitance, how much capacitance it has. Then we talk about capacitance, the same understanding, whatever we have there. All right, in farads we have to say, but we have to report in terms of farads per gram. That means now specific capacitance, capacitance specific to the mass. So specific capacitance people talk. Then they talk about the Coulombic efficiency. That means whether the charging and discharging time are same or different. So if the discharging is taking large time and charging is taking very small time, that is also not good. You have to see that this efficiency is near 100%. That means almost discharging and charging time should be small. So otherwise, this will be a problem that we will not be able to get a good value of this one. All right. The second thing is the energy, and now this is called specific energy. Again, energy with respect to the mass. So that same formula 1/2 CV square, but with respect to the mass of activated carbon on electrode. Some people report with respect to the total mass. Some people report with respect to the activated carbon which is there on a single mass. But normally a good practice is that for the energy and power, one should mention with respect to the mass of the device, whereas specific capacitance is an electrode property, so it should be reported with respect to mass of the electrode. Fine. So now I'll go quickly. This is because electrolyte characterization, all of you are familiar. So you make the film, then see the electrical conductivity, try to see that what is the temperature where it reaches a high conductivity. And after that, you work on that temperature. No harm in going at little higher temperatures. So we were actually working on little bit above 40 degrees initially, but now we have developed some other which is being used even at -10 degrees also. So here you can see that if the very first characterization people do is the cyclic voltammetry, and if the cyclic voltammetry is like of a rectangular shape, then we say that it's a good capacitor, charging and saturation, discharging and saturation, immediate discharging and saturation. So this makes a complete box-like structure. If the structure is box-like and it is featureless, then we say it's a process where there is no chemical reaction is involved. If some peaks are coming or dips are coming, that means chemical reaction is also happening. So if they are not coming, then we say it is a pure electric double layer kind of behavior. Now this is the coal core or the Nyquist plot. Normally, if you measure coal plot for a normal ionic conductor polymer electrolyte, then you get a semicircle followed by a straight line. that is corresponding to bulk and the interface. But here I already told that the bulk effect will not be seen here because there is no role of bulk. It's only interface which is coming. And that is visible here when you have the vertical lines in the Nyquist plot, which are seen here in this plot. So I'm just giving you a flavor that what kind of things should be called a supercapacitor. Say vertical line without any predominant circle is coming, then we will say that this is a supercapacitor. And then you can compare that how the other compositions were making the supercapacitor effect. And then we find that, for a optimized composition where salt content in the electrolyte and the nacicon content in the electrolyte is good, then that was leading to a large value of capacitance. Then the continuous charging discharging profiles up to 16,000 cycles could be worked out. And we could see that after the cycling, what is the interface? The solid-solid interface after the cycling is seen here, and it's quite intact after the cycling. That is also there. These are the charging discharging curves. So you charge and then you discharge, and you see that how much time it takes. These are called galvanostatic charging discharging cycles. All right. Then there was another approach when we said that when you have large amount of ceramics, you are reducing the amount of polymer and making a supercapacitor only based on ceramic. Now this is one of the important thing, because finally these ceramics are going to be playing role in batteries and supercapacitors. It's a concept actually, because polymer will also have a degradation with higher temperature. So you, in some way, after some time, you would like to get rid of polymer also from this one. So slowly, if you remove polymer from your matrix of the electrolyte, that means you are saying that you have actually, instead of adding ceramic nanoparticles to the polymer, now you have added polymer to the ceramic. So when polymer is added to the ceramic, electrical transport was dramatically very high, because now this also we have studied that what is the fundamental of this one. So a lot of work was already done on the fundamental ideas that how the electrical transport is taking place when polymer is added to the ceramic. That means polymer goes and ideally sits between the grains. That means it is actually acting like a coupling agent between the ceramic grains. So it is facilitating the intergrain transport there. And the conductivity reaches to more than 10 to the power minus 4 ohm inverse centimeter inverse in the same polymer film, which was shown here. So this is the ceramic and polymer type of film. So using a, simply first you do now here we have used some ball milling also. Because ball milling is required to mix the ceramic particles with polymer very properly. So if you just do it in a pestle mortar or in a magnetic stirrer, it will not work. You have to do using a proper ball mill, and using a ball mill, if you do it, then this is giving very good results. And these are the ceramic films actually. These are the predominant ceramic sheets where a little amount of polymer is added. All right. So this is with the polymer and ceramic approach also we have seen shown that it shows a very interesting result. Now this kind of potential versus capacitance cycles, if they are very symmetric, then we say high Coulombic efficiency is seen. So high Coulombic efficiency is very much required. That means the charging time and discharging time should be always almost same. And the final discharge curves also show more than 1000 watt per kilogram of power here, and reasonable amount of energy in the solid state. If you draw it now this solid interface still plays an important role here. So if you draw a current, a large current, then there is a polarization effect which happens there. This is a nature, right? We have to understand the nature. Solid interface will always have some kind of polarization, because ions, when they try to cross the interface or play some role at the interface, if they are moving very fast, then they will polarize and they will have their own electric field. And that is something which should be seen. And normally we observe that for low discharge current, polarization effects are less, and we get a very stable cycling. But if you do it for higher ones, then there is some issue and the capacity falls. At the same time, you also see that this can be improved. So yeah, one more role is the role of anions. So in batteries, we have seen that only cation should play a role, because cation takes part in the chemical reaction, be it sodium or lithium. But in supercapacitors, both the ions play a role here. All right, anions and cations both have to play a role. one electrode anion is going to play the role, and another electrode of the geometry, you have cations going to play a role. So you have to, be very careful in choosing the ions. In the batteries, when you say take a bigger anion. So bigger anion is going to help you because that will promote a single ion electrical transport. Bigger ion will stuck somewhere. But in supercapacitors, you have to say that you have to choose a smaller ion. Of course, it should not chemically react and subject to other conditions. But this anions, they are smaller in nature. They are showing better results. So we see that if you have lithium chlorate, which is the smallest cation, which has the smallest cation, it will perform better. It will show a good result. All right. Third issue is the sodium ion systems also. So this is true for sodium ion also, that we can prepare the all solid state supercapacitors, and the very similar method we have used. But here the added particle is Nasicon. This is called NZSP. So NZSP is a Nasicon which was John Goodenough's discovery, and he got Nobel Prize for this electrode development, along with the contribution to the solid state ionics also. And here, using these Nasicons, we could achieve very high ionic conductivity in sodium ion based polymer electrolytes. And these are solid polymer electrolytes. I'm repeatedly saying that these are not gels. They do not have any liquid content at all. And these can be used nicely again in such devices. So that sodium ion supercapacitors were also developed, and their cycling was tested very nicely. They are, in fact, a nice stability is seen for sodium based supercapacitors up to 10,000 cycles. Our recent results have shown that there is no chemical reaction which takes place. There is a good stability of voltage. For example, here potential versus cycle number, you see a good stability. It doesn't fall actually. And potential versus CS at different cycles also show a very good Coulombic efficiency. Stable cycling, and we can also see that appreciable capacitance and high energy density also is seen. And Nasicon content plays an important role here. That is what is the message which comes here. Last topic, 5 minutes more I'll take, and I'll be winding up. Interface is still important, and solid-solid interface is something which requires more understanding, more physics, and more support from the theoretical input also. And you have to play with this interface. So one of the ways people do at the interface is by incorporating some kind of butter layer now. All right. The way you put butter between two braid slides and braids के बीच में you put butter, उसको लगा देते हैं, चिपक जाएगा. That way, nowadays people are using various butter layers between a electrode and electrolyte. Using two solid electrolyte and electrode को चिपकाना है, so you have to use good butter layer. इसका reason क्या है? Reason is that as I have shown schematically in this picture, the activated carbon is unable to be utilized very properly when you have a solid-solid interface. Why? Because still, wherever the polymer is able to go, that place is able to reach. But then there are many holes and pores where solid electrolyte cannot reach the way liquid used to reach. So you have to find a way that how the effective area of the activated carbon can be utilized without using the liquid. Now here the butter layer should not have liquid. अब कोई इसमें एक drop ionic liquid डाल देगा तो सब काम हो ही जा रहा है. Suppose you put little bit of ionic liquid in between and say it is a butter layer, fine, very good interface. But no, we don't want to do that at this point of time. We want to say that no, what is the best possible effective use of solids? Being a physicist, we should explore the nature. So what we did is prepare the electrodes using some part of that polymer which was also there in the electrolyte. So what happens, some polymer is there in electrolyte, some polymer is also there in the electrode. So now it makes friendly business between these two. It makes a good bridging behavior, good coupling between the electrodes and electrolyte. And this coupling behavior can be further improved by changing the content of the polymer and This is now a new area in which one can think about that if polymer goes in the activated carbon material, what happens? So here you can see in this SEM diagram, the polymer electrolyte is going in this one, in this in the pores of the activated carbon. So it goes there, then it is also having salt. That means it is able to make a tunnel for the salt ions to go into the pores of the activated carbon. That is the beauty of this one. This effect was very dramatic in providing interesting properties, stability of the solid, all solid state supercapacitors. So the properties could be further improved. But I'm not saying that here it's a conclusive statement. Many more studies are required to be completed. Many understandings have to be developed here. It's a very preliminary result we reported in this journal, Batteries, and we said that this can be further improved. We can make the process more faster. We can make the process more stable. The cycling performance becomes stable when the polymer goes into the electrode. A very honest and simple work which we presented there was appreciated, and with some very positive remarks that a lot more can be done in these directions, and we are trying to do this. All right, so my final slide now. So what is that we have done? We have developed all solid state supercapacitors using polymer electrolyte films. Which are those films? These are the polymer electrolyte films which are hybrids in nature. They are added with activated carbon. They are added with some kind of ceramic fillers, which are ion conducting fillers in nature, like nasicons, garnets. All these things we are trying. All sorts of sodium and lithium and fast ionic solids we are adding, and different students are working and contributing in that direction. This is the beginning of a work, and we have some properties which are better than the gels also. When I say better than the gels, I don't want to underestimate the contribution of those who are working on gel polymers for years. I have to say that there are many advantages of using the gels even now. You can make flexible devices because gels are also extreme, but then you have to progress now. 20 years gels are being used for last 20-25 years in the double layer capacitors. Now we should go and see the effect of solid polymer electrolytes also, and then we will see the effect of pure solids. So we are also trying for a pure ceramic and its contact with pure activated carbon using different ways, different techniques. So interface has to be improved, and these power devices are the way all solid state batteries are also low power devices now. They are also low power devices now. We have to be honest in saying that it is a nature. You can't challenge nature beyond its limits, but we have to try to extract the best out of it. Possibly the large surface area can give better results. Possibly the pseudo capacitance behavior will also be very interesting here. We are working on pseudo capacitors also, and we are also working on the hybrid capacitors using these two. More emphasis is on the understanding physics behind the processes, because students should be trained in the physics behind the processes. The fabrication part can be learned whenever they go to any big lab, but the understanding and the training of how the physics and chemistry of the material should be looked into and understood, how an authority can be developed on a particular scientific idea is more important for us who sit in universities and do. We do have patents, but our interest is more towards training the people and taking them to the next level and imparting this knowledge, whatever we have received from our seniors, to the next generation. With that idea, I am working here. So thank you very much for your understanding and precious time. I'll be very happy to answer questions if there are any questions.
Now the session is open for question and answer.
Pranam. It's online now.
I have one question. Yeah, though you are working to develop super is it there any work is going on to how we store the electricity.
There is a lightning, and is it possible to store that energy, because this is a tremendous amount of energy? If that we store, we can use it in domestic purpose also. So is it any research is going on in this field?
I could partially listen to your question because voice was shaky. What was the initial part of your question? Could you please repeat? Ikbar.
I have a question that is it any device or a super capacitor developed to the lightning energy?
लाइटनिंग एनर्जी, अरे वो तो हमारा बेंजामिन फ्रैंकलिन वाला एक्सपेरिमेंट अगर आपको याद हो, उन्होंने काइट लगा के और राइट वी यूज्ड टू स्टैंडर्ड. So yeah, I mean,
क्या मैम करें? क्या स्पीकर पे था क्या?
Can I speak?
Sir, Deepmala.
Yeah. So hello, am I audible?
Yeah.
तो मैं कह रहा हूँ कि yes, that is quite ambitious to talk about getting sudden energy and storing it to a place. People have been trying for 400-500 years using that Leiden's jar experiment when Benjamin Franklin used a kite, and that using that kite he tried to collect that lightning into a jar, so that energy in a jar, that was a capacitor actually, which was called Leiden's jar, if you remember. And many people died in such experiments. People sacrifice their life for such experiments. Right now, the idea is that to use this solar energy very effectively. Everywhere, particularly we sitting in India, have huge radiance of solar energy. So if the solar energy falls on our roofs and our places, like myself sitting in Rajasthan, aap log MP mein hai, we have almost that good intensity, almost vertical lines are falling here, and solar panel power should be generated. That is number one. And then that solar power, whatever is generated, should be effectively used and stored using supercapacitors and batteries. So you can have some solar cars where you can have combination of batteries and supercapacitors with solar energy. We can have effectively solar grids, microgrids, where we can talk about generating the power using the solar energy and storing the power in battery and supercapacitors or their combinations. So all these non-conventional energy sources which are there, they should be used for generating the energy, and these electrochemical energy storage devices can be used for storing the energy. This should be tried, and in fact we have in India since 2008 the solar energy mission, and after 2016 using the Niti Ayog's work on energy storage mission. So we would like to, India would like to be, using these things very properly. And by 2030, we will have 75% of our market to be captured by the electric vehicles. So that is the idea. But of course, the question which you asked is quite ambitious. That a sudden energy which falls, can it be stored to the device? Well, such a huge energy will have huge, million electron volts of energy, and that energy can't be stored at one small place, because every material will have its own, melting point and thermal stability. So such huge energy should be disseminated and then can be stored on smaller and smaller devices. Possibly in future, those things can be planned.
Thank you, sir. Thank you. There are people are thinking to store the natural energy, form of the energy, solar energy in case of the capacitor. Now, after some time, maybe people generated super capacitor that store a higher amount of energy, natural energy, and that we will use in future. Thank you very much, sir.
Thank you so much, sir, Ansuman Dalve, sir, for your enlightening lecture on solid state supercapacitor, fundamental fabrication strategies and challenges. This talk will surely motivate participants on this exciting field in future. Thanks. Thanks once again, sir.
Thank you very much. And my regards to Professor Verma Gupta ji, Ravindra ji, कैसे हैं आप?
बहुत अच्छा, thank you so much, nice talk.
Thank you sir, thank you very much.
बहुत बढ़िया था सर, मजा आ गया, बहुत दिनों के बाद आपको सुनने का मौका मिला.
Thanks to the organizers, really it is a good, we are meeting together.
It's very nice sir. And I have seen Mohanji's work and his lab and the passion in a very small limited resources. He has, kind of work he is publishing, and he is very consistent in publishing good quality papers. तो हमको ये बहुत मोटिवेटिंग लगता है कि हम लोग यहाँ पर हैं और हम लोग जिस तरह से मतलब आपके ग्रुप ने मुझे बहुत मदद किया है. प्रोफेसर आई वेरी हाई रिगार्ड्स फॉर योर गाइड राकेश अग्रवाल सर. उन्होंने हमको जब मैं यहाँ पर अपना लैब छोटा सा शुरू कर रहा था तो आप सभी लोगों के गाइडेंस से हमने वो इंस्ट्रूमेंट करना शुरू किया जो छोटी जगह में हम लोग ले सकते थे उस लिमिटेड बजट में. सो आई हैव वेरी हाई रिगार्ड्स फॉर ऑल ऑफ यू हु हैव रियली कंट्रीब्यूटेड एंड वेरी कंसिस्टेंट वर्क. और सबसे इम्पोर्टेंट ये है कि आप लोगों के जो पेपर्स हैं वो बहुत फंडामेंटल वर्क पर होते हैं. उसमें समझने के लिए बहुत कुछ होता है. मतलब ए न्यू रिसर्चर शुड फॉलो. फॉर एग्जांपल I would say प्रोफेसर रविंद्र गुप्ता जी का एक वो जो रिव्यू आर्टिकल है बहुत अच्छा रिव्यू आर्टिकल.
कंपोजिट पे जो रिव्यू आर्टिकल
कंपोजिट पे जो लिखा है, I always give to my PhD students that you please read these things because this is a consolidation of all sorts of good work in this field. तो
solid state dynamics का पूरा है.
बहुत अच्छा लगता है. और ये भी कि अभी तक हम सारे लोगों ने solid state dynamics को छोड़ा नहीं है.
Yes.
Working on
नहीं छोड़ा भी नहीं है.
This is important. क्योंकि लोग फ्रस्ट्रेट होकर लिक्विड में घुस रहे हैं. I would like to see that we still continue on solid state and justify our presence being a physicist there. मुझे लगता है.
True.
Thank you very much, sir.
Thanks a lot, sir. मेरे तरफ से भी और ऑर्गेनाइजिंग कमेटी की तरफ से तो है ही.
I'm always there. I'm always there for you.
Thank you so much. Nice presentation.
Thank you, sir. Your inputs are important. Always give me whenever. Thanks.
Okay, sir.
I, Rashmi Priya Topo, Assistant Professor of Physics in Government Nagarjuna PG College of Science, Raipur, Chhattisgarh. It's my privilege to introduce Dr. Ravindra Kumar Gupta, Sir, Assistant Professor in King Saudi Arabia. Sir has done PhD from Pandit Ravi Shankar University, Raipur, in Solid State Ionic Material Science. Spent more than 25 years in research and academics. Research area of interest is solid electrolytes and electrodes for renewable energy source and batteries. Also in nanomaterial for energy application, more than 33 conferences and 86 plus research paper published. So I would like to invite Dr. Ravindra Gupta sir for his talk. Very welcome, sir. Sir, you can share your screen if it is required.
Can you see it?
Sir.
Yes, sir. दिख रहा है, sir. Yes.
Is it okay?
Yes.
Okay.
Sir.
Good morning. I think in India it is morning. Good morning, everybody. Thank you so much to the organizers. As Dr. Mohan and Dr. Ansuman told, my area is solid state ionics. And I'm still working on this area because we have a lot of problems and we want to solve using the solid electrolytes. So, but today I will talk about the solar cells. Being a person of the solid state ionics, because we are using the solid electrolytes for the Dyson style solar cells. So I will discuss little about this also. So this is the fundamental things actually. And just like a small review. And I'm also learning actually because of Mohan. He told me about solar cell. So I told, okay, I will try. And so I prepared the this notes, this presentation file. So I'm also learning with all of you. So this is the my content of the talk, sunlight, solar cells, and then I will talk about the different types of solar cells, and then about the confirmed solar cell efficiencies. So sunlight, what is sunlight? This is the source of energy. This is a type of renewable energy resources which is available plenty, and this is the actually it comes from the sun. So we say sunlight, and it is a part of the electromagnetic wave spectrum, and it is from the 400 to 700 nanometer. We also have ultraviolet as well as infrared. So if you see this sunlight on our earth, so you can you can see here, this is for the this is for the black body radiation on our earth. And then this is the sunlight, that yellow color sunlight without the atmospheric absorption. At the sea, you can see this is the red color. So we want to utilize this light in the visible region, if possible in the infrared region and UVA region. So this is the target. And you can see here we have different standards. So we use AM 1.5G, means with angle 48.2 degree for the solar cell application for standardization. So this is the thing. And this is the world solar energy map. So if you see, if we are on the Tropic of Cancer or on the Tropic of Capricorn, or in between these two, we have high sunlight irradiance. It's very, very high. And for the Saudi Arabia, for example, for India, for Tunisia, and in Sahara Desert, actually in USA, like that, we have so much irradiance. So it is 2 megawatt per hour, 2 megawatt hour per meter square. It's quite high. So we want to utilize this sunlight irradiance. So we have one device known as the solar cell, which is also known as photovoltaic cell. And this is a type of renewable energy sources. So what are the advantages? Here we have sunlight as a fuel, which is widely available, accessible, infinite. So no emission, no combustion, no radioactive waste. See, this is the advantage. Because fuel is free, so no, low operating cost. It has no moving parts. We can operate around in the ambient condition, means maybe 20 degrees Celsius, 30 degrees Celsius, 40 degrees Celsius, no problem. High reliability of solar modules. Manufacturer guarantees over 30 years if you have the silicon-based solar cells and gallium arsenium-based solar cells. Rather predictable annual output. Modular, can be small as well as large. Any can, we can make any size, no problem. Can be integrated into new or existing building structures, like that. It has so many advantages, but it has some disadvantages also. It is intermittent. The sunlight is intermittent, okay? And fuel is, source is diffused, okay? Density is less. High initial cost. At the beginning, we have to put a lot of money. And if we have the silicon-based solar cells, we get back our money within 3 years. But for the Dyson-sized solar cell, it is less than 1 year. Unpredictable hourly or daily output. Of course, for the year, we can predict, but for the daily basis, we can't do it. And efficiency is still not so good, and storage is a big problem. These are the basic problems we have. So what is the basic for the solar cell? So if we have any semiconductor material, so there we have one valence band and then conduction band. And because of the, if we have photon, which has energy greater than the band gap energy of the semiconductor, then because of the absorption of the photon, this electron get excited from the valence band to the conduction band, and then this electron migrates through the external load and gives the power to the device. So this is the basic thing, basic physics actually. But what are the solar cell materials? Which type of solar cell we choose? So the basis is how well the absorption characteristics matches with the solar spectrum, and also the cost of the fabrication. So these are the two requirements for the solar cell materials. So we have different types of solar cells. Silicon nowadays available everywhere. We have third, fifth elements based solar cell, chalcogenide, quantum dot, sensitized solar cells, organic solar cells, perovskite solar cells, Dyson-sized solar cells. And I will discuss little more about the silicon-based solar cells, because this is the base of our solar cell. Then we have different type of solar cells. And being a person of the solid-state ionics, we are utilizing the solid applied for the solid-state Dyson-sized solar cell. So I will try to discuss if I have time. So silicon-based solar cell first. Why silicon? This is the question. Silicon is abundant. You know it. It is abundant. Everywhere we have. In terms of the sand, SiO2. Absorption characteristics of silicon matches fairly good to the solar spectrum. Here you can see band gap energy is around 1.12 electron volt. This is very, very good. Silicon fabrication technology is well developed. As I told earlier, quantity is abundant, non-toxic, environment friendly, and this is from the fourth group. Okay. And when we add the third group into the fourth group, we have p-type material because of the holes as a majority charge carriers. And when we add fifth group element into the silicon, we have n-type material where electrons are the majority charge carriers. So if we make a cell like this, here you can see this is the p-type layer, this is the n-type layer, and then we have the pyramid, inverted pyramid structure as an anti-reflective layer, then metal grid to collect the current. Here we have the base, back surface field, metal contact. So when we have sunlight irradiation, because of the electron hole formation, we have the current, and which passes through the this metal grid, comes to the passes through the load and comes to the metal contact. So this is the basic thing. So here there's one thing I want to say you. This is thick. It is around 300 micron. This is around 0.35 micron. Okay. So this is the basic phenomenon. Because of the PN junction, we have the depletion region, also known as space charge region. Here we have no free electron and holes. Here we have electrons in majority and holes in minority. Here we have holes in majority and electrons in minority. So what happens when we have the radiance of the sunlight? We have electron hole formation everywhere, but useful is in this section, in the depletion region. So this electron migrates toward the this grid, and this hole migrates towards the this side. Okay, and then we have electron migration from through the load. So this is the basic, as I told you earlier, this is the basic thing. And we have recombination also, 3 types of recombinations: single level trap because of the impurities, radiative from valence band to conduction band, from the conduction band to valence band. Then we have the agar type of recombinations also, which actually recombination is not good at all. So we have to reduce the recombination. And this is the model. So we have 2 types of recombinations. One from the N-type region and P-type region. Another is from the depletion region. So I01 from the N-type and P-type region, and I02 from the depletion region. So it generates dark saturation current, and does the recombinations. So we have, this is the expression for the current, total current. This is the open circuit voltage. When we have no current, then this is the open circuit voltage, which is the function of ISC and I011 also, and it depends on temperature as well, you can see. So here, this is for the model. Here, if you see, thickness is for the N-type region, 0.35 micron. For the P-type region, it is 300 micron. And doping density is here, it is highly doped. It is 10^20 centimeter per cube, centimeter cube. And this is the 10^15. Surface recombination is, it is, you can see, low, but here is very, very high. Minority charge diffusivity is here very high, but here low. This is the advantage of the BSF, the back surface field. And the lifetime of the minority carrier should be less in the N-type region and high in the P-type region. So we have that thing. And the diffusion length should be lower in the minority carrier in the N-type region, and it should be high in the P-type region. So these are the basic requirement. This is the characteristic solar cell. It is the solar cell characteristics IV curve, and you can see it is flat. If it is ideal condition, you can see it is just like a box like this, but in the actual case we have like this. So here we have 3 parameters: ISC, VOC, IMP from this point, VMP from this point. So here we have 3 parameters to get the efficiency, fill factor, ISC, and VOC. So, and fill factor depends on this is just a ratio of the VMP, IMP divided by VOC, ISC, and efficiency, you can see. And in general, we measure the efficiency at 1000 watt per meter square or 100 milliwatt per centimeter square. It is known as 1 sun or AM 1.5G. This is the standard condition as I defined earlier. But that is the ideal condition. We also have the resistances, and this is the current. You can see we have 2 types of resistance. first the series resistance due to the movement of the charge carriers through the emitter to base of the solar cell, contact resistance between the metal contact and silicon, the resistance of the top and rear metal contacts, as well as wires also, leads also. And because if we have high series resistance, you can see fill factor is very low. So the series resistance should be as low as possible. It should be 0. Okay. So if we have 0, then we have very good efficiency. So this is the thing. And then next is what happened? Hello. Hello.
Yes, sir, you are audible.
Okay, it got stuck actually. Okay, now working. And then we have the shunt resistance. Here you can see the shunt resistance should be, this is the shunt resistance. It should be as high as possible. If it is low, you have the current will pass through that low resistance. So it should be as high as possible. It should be infinity actually. So what happens when we have the low resistance? So in this case, the current diverges from the shunt resistance and reduces the voltage and also reduces the current. So which is not good at all. So actually this is due to the manufacturing problem. This is the manufacturing problem, not from the solar cell design. Okay. So these are the parameters. What is the effect of temperature? So when we increase the temperature, we increase the intrinsic concentration and also increase the dark saturation current because of recombinations. So it reduces the open circuit voltage. Means high temperature is not good at all. For the silicon-based solar cell, temperature should be low. Low means it should be in the ambient condition. Maximum 40 degrees Celsius, not high. But in Saudi Arabia, temperature is very, very high. 50 degrees Celsius, several places. So it's not so good. That's why Dyson-style solar cell is very, very good. Higher temperature, higher current, higher open circuit voltage for the Dyson-style solar cell. And this is the limit. If you see for the PN junction diode, for the black body radiation, you can see here, it is A, unconcentrated. So it is around 30%. For the full concentrated, it is around the B, it is 40.7%. For the AM 1.5G, it is around 32%. This is the limit for PN junction. So we can get the highest conversion efficiency of 32%. This is our limit for the single junction PN solar cell. And this is for the 1.1 electron volt. So here this is the solar spectrum with wavelength. This is the quantum efficiency. So here you can see it is very, very low because of the front surface recombination. And here we have less because of the, this is the ideal condition actually. This is the ideal condition. It should be like this only, but this is not true. Here we have the very, very low because of the front surface recombination. Here we have the reflection as well as the low diffusion length. So we have to reduce the reflection. The loss should be very, very low. And the diffusion length should be high as much as possible. And the red response is due to the rear backside surface recombination, as well as the long wavelength. If we are going towards the infrared, so naturally energy is less. So naturally the photon conversion to electricity will be less. And if it is less than the band gap of the semiconductor, naturally no conversion. So what are the key factors to design a solar cell? So here you can see N ideal means the semiconductor materials of the band gap of the semiconductor material should be matched with the solar spectrum. Means it should be around this region, 1 to 0.75, not 0.75 actually, around 1 electron volt to 2 electron volt. This is the condition. Optical losses should be as less as possible. It should be very, very low. Okay. So there should be no grid shadowing, no reflectance, no absorbance. Okay. So it will and the maximizing the optical thickness of the solar cell. Okay. Another thing is the series resistance and shunt resistance should be low, and therefore the fill factor will be high. And minimizing the bulk and surface recombination rates, so it will increase the open circuit voltage as well as short circuit current. So these are the parameters to improve the solar cell efficiency. So now I'm going to talk about the amorphous silicon-based solar cell. This is the configuration. Here you can see this is the glass. I have 20 minutes left. So this is the glass. On that we have the front transparent conducting oxide, which is either ITO, indium doped SNO2, or aluminum doped zinc oxide. Then we have P-type material, which is very thin. You can see here. And this is the amorphous silicon carbide or microcrystalline silicon hydrogenated. And then we have intrinsic amorphous silicon here. And then we have N highly doped amorphous silicon, or the microcrystalline silicon. And then we have the rear TCO. Then we have back contact, which is made of silver, or nowadays we are using aluminum. So this is the basic configuration for the amorphous silicon-based thin film. And this is the microcrystalline silicon-based thin films. Here, this is the glass. This is the first generation. This is the second generation. So here, this is the, we are using polycrystalline silicon layer because it is cheaper also instead of glass, amorphous silicon. So here you can see this is the back reflector on the glass. Then we have N type of layer, the intrinsic polycrystalline material. Then we have P type of layer. And here we have surface structure. Okay. This is the inverted pyramid style. It acts as a anti-reflecting coating. Okay. So, and then we have ITO, and then we have grid to collect the electron. So this is the microcrystalline structure, thin film, of course. Then we have another structure. So actually in the market at present, we have this type of solar cells at present. We have amorphous based also, polycrystalline based also. But nowadays, in the market, we have PERC based conditions. So what is PERC? This is the passive weighted emitter and rear contact cell, PERC. What happens? This structure reflects photons back into electron layers, causing the cell to produce more power and preventing electron recombinations. These two benefits result in increased energy conversion efficiency and decrease heat in solar modules. So if we have actually recombination, as you saw, we have phonons because of the heat, and which is not good at all. So if we have the recombination, so naturally low heat generation. So PERC helps. So here we have passivation. Here you can see, here we have passivation. Here we have passivation. So this reduces the recombination with the minority charge carriers. Minority charge carrier here as well as the minority charge carriers in the P region. Okay, so this is the cell design. You can see here, this is the front contact made of silver, and nowadays we are using TI also. This is the anti-reflecting glass, SiO2. This is the quartz glass. This is the inverted pyramid style. Then we have the negative N type of material. Here you can see, very thin, very, very thin. Then we have P-type silicon layer here. These are crystalline material. Okay. And then we have local back surface field. And then we have a passivation layer, which is made of alumina or SiO2. Then we have dielectric capping layer, silicon nitride. Then back contact made of aluminum. So this is the structure, but it is little complicated. But we can use the manufacturing plant, what we have for the normal solar cells manufacturing system. So, but that's why it is cheaper. We don't need much conditions for manufacturing expensive manufacturing plants. Whatever we have available, we can use. This is the another structure known as TOPCon cells. Nowadays it is also coming, but at present contribution is less. So here, tunnel oxide passivated contact. So what is the, this is similar to your PERC cell, but here you have little difference. This is the ultra thin tunnel made of SiO2. It is very, very thin on the P-doped silicon. This is the polycrystalline. And then we have the aluminum. And then we have the, this is the then N-type polycrystalline material. No, sorry. This is the crystalline material. And then we have highly doped P-type material. And then we have the alumina or silicon oxide or magnesium fluoride. Then we have either silver or titanium or mixture actually. Many times we use Li also nowadays to reduce the cost. So this is the another type known as IBC cell, integrated back contact cell. So this is here you can see it is similar to PERC, but here we have P-type, N-type like this, alternative, okay, at the bottom only. So here we have no grid. Can you see here? We have no grid. All grids are at the bottom. So what happens, advantages here, we have no shadowing effect, no contact effect, okay? And the series resistance is less, naturally, because all are on the bottom. So this is the advantage. And this is the structure you can see here. This is the N-type material, highly doped. This is P-type material, highly doped. Again, N-type, like that, it has a series, N-P, N-P like this. And in between, you have, this is the silicon oxide. Then we have grid, metal grid. And here, this is the P type of amorphous silicon, and this is N type of amorphous silicon. So we are using here amorphous silicon as well as crystalline silicon also, doped silicon. So two things together. So cost is less naturally. Okay. So here you can see the structure more clearly. This is N plus, this is BSF, this is P type emitter, N plus VSF, that's metal finger, like that. So both contact layers are at the bottom. So this reduces the contact resistance. So this is the advantage. Next is, it gets stuck actually. I don't know why. Okay, now coming. These are the advantages as I discussed, but there's a complications. The current flow of carry is done in 2 dimensions, but when we use standard cell or PRC, it is one direction only. The efficiency of the IBCL is deeply related to the BSF lifetime and the front surface recombinations, demanding higher quality silicon wafers with a longer carrier lifetime. So these are some complications, but very easy. And the future is on the heterojunctions technology. After maybe 2030, we will be having this more in the market. So here you can see this is amorphous based with the this amorphous and the crystalline based both. So here if you see, it is 2 types. This is the HBC type, heterojunction with integrated back contact. It is IBC actually, heterojunction with IBC structure. This is heterojunction with intrinsic thin layer style. So we had 2 styles, and of course this is very, very easy, better than your previous one. So this is improving. It has low temperature coefficient, easy to make. So low light in performance also it has. Life is more. And now I will talk about the efficiencies available with the in the market. So this is for the crystalline silicon based solar cells. This is from the NREL USA. So here if you see silicon based solar cell, this is single crystal with concentrator. There's one more thing. If we have concentrator, if we focus the sunlight on the solar cell, we can increase the photocurrent. This is the advantage. But condition is the temperature should be low. So we must have cooling system also with the concentrator. Then only we can increase the current. Otherwise, it will decrease the voltage. This is the problem. So this is for the single crystal. This is single crystal with non-concentrator. Here you can see this is multicrystalline. This is multicrystalline. This is for HJT. Here you can see is very, very high, 24-26%, something like that. And this is from the Green et al. Green, Martin Green actually group records the efficiency, and they publish every 6 months. So this is the latest one, published recently in 2023. So here you can see these are the standard. These are the reported and tested actually. So this is for the silicon-based solar cell. Areas you can see very, very high. This is from the company Longi, N-type HJT. This is 26.8%. But when we have directionally solidified wafer cell, it is 24.4%. But this also area is very, very good, you can see. But for the thin film, this is 21.2. But when we have mini module, thin film, this is 10.5%. This is from company CSG Solar. Here, the thickness is less than 2 micron. Okay, the thickness is very, very thin. What about the amorphous silicon? You can see this very, very low, 10%, 11%. And this is for a small area. And when we increase area, it will be further less. What about the other systems? Actually, the best from other groups. So here we can see for area 4 centimeters square, 25%, like that you can see. This is for 244, 24%. So, and for large crystalline, this is 26%. So here you can see it's very, very high, very, very good. That's why silicon-based solar cells are very promising. Everywhere we are using. And the life lifetime is more than 30 years. It can go maybe 50 years also, no problem. This is the advantage of the inorganic materials. Next is the fifth elements based solar cells. So here we have gallium, arsenium, gallium, this is multicrystalline. We have indium, phosphorus, gallium, indium, phosphorus. And if you see this thin film, thickness is in nanometer. It is 10 nanometer. Gallium, arsenium thickness is very, very less, 10 nanometer. And it is on the substrate, germanium. Okay. And so structure you can see is very, very good. But problem is the arsenium. This is actually, it is toxic material. But of course, thickness is very, very low, 10 nanometer. So it is good, but we need 10 nanometer fabrication means you need very sophisticated instrument for manufacturing. This is the problem. And gallium, Ga, this is another problem. It's not so plenty, so expensive material. That's why when we need for the space application, when we have very less space, when we need very light, then we go for the this solar cell. And you can see for thin film efficiency is very, very good. 29. Of course, area is very small. For the large scale, you can see 4%. Sorry, 18%. This is 4 centimeters square. Next is the this is the trend. This is the life of the these solar cells from the NREL. Then we have the chalcogenide based solar cells. So here we have the copper, indium, gallium, selenium, selenide based CIGS, very popular. Cadmium, tellurium. These are the thin films. Okay. So here, this is the structure you can see. Let me check the timing. I have more mind. I have 3 minutes. So here I have CIGS. Here you can see it's very, very good, 23%. When we go for the submodule, it is 665 centimeters square. It's very attractive, 19.8%. For the CDTE, 21%. For CJT, SSE, like that. Here you can see. So that CGSE, you can see very, very good. And this is the trend. Then we have quantum dot sensitized solar cell. Quantum dots are very, very small. It is in nanometer scale. It absorbs the light. It absorbs the light. And here, semiconductor is the TiO2. Semiconductor is TiO2. But TiO2 band gap is very, very high, 2.2 electron volt for the anatase phase. So that can't absorb the light. So naturally, we need some material which can absorb the light. So here, quantum dot, which is in nanoscale, in 1 nanometer, like that, 2 nanometer, 3 nanometer. So which absorbs the light. And this here we have the HTM, whole transform material, spiro, and then we have P dot to collect the electron, and here we have the P dot SSS. So this here you can see to collect the holes. Like that we have the structure, and this is the trend. At present we have 18%. Still very, very good quantum dot cell. Then we have organic solar cells. The advantage of the organic solar cells, it is flexible and it is organic. So it is cheap also, economically easy. So this is the structure, and this case you can see efficiency is nowadays very good, 15.2%. Of course, area is less, 1. But when we increased 19 centimeters square, it is approximately same. And when we increase further, it is 11.7%. It is equivalent to your amorphous based solar cells. So this is the advantage. Then we have nowadays perovskite based solar cells. This is the structure you can see. And for the perovskite based solar cells, we use TiO2 to have the perovskite material, methyl ammonium lead iodide. But here PB is not good. It is toxic material. So people are trying to replace the PB by another material. I think I have now 5 minutes left. So I will try to finish as much as possible within 5 minutes. Then we have the we have HTM material to get the electron in holes, and then we have gold material like that. This is the structure, and we have light from the bottom, from here side, this side. So here these are at present, this is very, very popular in the research field, and efficiencies you can see 23.7, and when you go for the mini module 26 centimeters square, it's very, very high. But problem is for the perovskite based solar cell, the stability. People are still trying, facing problem to stabilize the efficiency. This is the basic problem. And till now, it has been reported 25.7 for a very small solar cell from the Korea UNIST Ulsan. And next, this is the trend you can see. And then I will talk about the Dyson-style solar cell. This is very, very, you can see it has so many advantages. It uses no toxic material. It uses low cost materials. It is ecologically as well as biologically benign. No expensive equipment for manufacturing, engineering into flexible slits, short payback time. For the when you go for the silicon-based solar cell or CDSE or any type of inorganic material-based solar cells, you have incident angle-based efficiency. Means the solar cell depends on the angle of incidence of your light. But when you have DSSC, Dyson-style solar cell, you don't bother. It is free, okay? Doesn't matter. And when you have high temperature, the efficiency will be more, okay? And when we have diffuse condition, efficiency will be more. So these are the advantages of the Dyson-style solar cell. And this is the structure you can see. Here we have electrolyte, maybe liquid or solid, which is the which has iodide, triiodide redox material, or cobalt-based redox material, or copper-based redox material, which is sandwiched between the working electrode, which is made of dye-sensitized TiO2. As I told you earlier, TiO2 band gap energy is 2.2 electron volt, which is very high, which is not good to absorb the sun, the photon. sunlight photon. So naturally, we need a dye. So dye function is to get excited from the HOMO to LUMO, give the electron to the current collector that passes through the current collector at the bottom side, which goes to the, then here we have the triiodide. The triiodide collects the electron and gets the into iodide, in the iodide. So this is the basic thing. So, and this is the mechanism as I told you earlier. And what is the role of electrolyte? So it regenerates dyes via the oxidation of iodide into triiodide at the working electrode. It reduces triiodide into iodide at the counter electrode, and it inhibits the back electron transfers, like recombination. We don't want any recombination, which is not good for any type of solar cells. So these are the liquid electrolytes, and we have at present 11.4% for this type of electrolytes. This is iodide triiodide based electrolytes. When we go for the cobalt based electrolytes, efficiency is better than this. Even we have 14%, 14.3%. So, but problem is these are liquid electrolytes. As Dr. Ansuman Dalvi told, we don't want liquid electrolyte. Why? Because we have so many problems. Reduction in long-term stability, high pressure at high temperature results in backage of sealing and leakage of solvent, as well as the manufacturing problem. So we don't want. Okay. So here you can see, instead of using single dye, we are using several dyes to cover the spectral region. Okay, so here we have SM342, Y123, then it gave 12.7. If we have only 7 SM342, it is less than 10%. Like that, we have to increase by optimization the dyes. But in the for the research, for the lab, in lab we use single. For example, I'm using only N719 or Y123. So this is the mechanism. You can see we have several dyes. So it goes like this: electron from the up to here, TiO2. This is the LUMO level of the TiO2, and this is a HOMO level. So from the dye, it goes to TiO2, and this is the characteristic solar cell pattern. This is from the Kiej et al. And here you can see the efficiency for the dye-sensitized solar cell. The highest reported value is 11.9. It is from the company SAR. And when we go for the mini module, which has 26 centimeters square, it is nearly 11%. Good. And when we go for the mini submodule, it almost 400 centimeters square, it is less. And from the EPFL, they have reported 12.25%. So this is the values, and here this is the trend. So in our lab, we are using the solid polymer electrolytes to synthesize, to fabricate the solid solid state dye-sensitized solar cell. And these are the reported things people have done, and the blue color shows the what we have done in our lab here in Saudi Arabia. So these are the materials, and I'm not going to discuss this thing now. Here you can see it's very simple. We are using the blending of PEO and succinonitrile, polyethylene oxide and succinonitrile as a matrix, and then the iodide triiodide. For iodide triiodide, we are using iodine based material, and then iodide, like that. But it has problem. It absorbs actually the sunlight at 430 nanometer. That's why now we have moved to the cobalt-based system, and this is very, very good. So here, conductivity measurement, conductivity should be equivalent to the liquid electrolyte. This is the target. So this is the conductivity measurement. And then temperature dependence, it should be stable in wide temperature range. So activation energy should be less than 0.3 electron volt. And then it should be amorphous. And then you can check by different ways, amorphosity by DSC also. And then it's stable, it should be thermally stable. And then we go for the solar cell fabrication. But here you can see efficiency. In my case, when I use PEO, efficiency is very, very less because of the interfacial problem. We don't have very good connectivity between the TiO2 dye and electrolyte. This is the problem. That's why when we use succinonitrile, it helps, but still you can see efficiency is not good. The problem is the interfacial connectivity. And these are the IPC spectra. It's very, very good. You can see. Then we model it, this Nyquist plot, and then we get the resistance. Like that, we do some extra work. And now at the concluding section, I will show the confirmed solar cell efficiencies of the actual solar cells, terrestrial modules. And for different conditions. So this is non-concentrating. This is the actual solar cells, okay, in the market by different companies, Kaneka, Hanwha, China. This is Alta Devices, Solar Frontier, like that. So several companies. So here for the silicon-based solar cell, you can see 24.4%. Okay, can you see area? It's very, very big. Okay. For multi-class, 20%. For the gallium arsenium, this 25%. For the CIGS CD-free, it is 19%. Thin film, 19%, the CDT. For the tandem cell, 12%. For the perovskite, 17.9%. For the organic solar cell, 8.7%. Okay. For the multi-junction, as I told you earlier, if we have multi junctions, if we have multi semiconductors according to the band gap, then we can collect the all wavelengths of the sunlight. Then we can increase the efficiency. So here you can see efficiency of the indium, gallium, phosphorus, upper section, middle section, gallium, arsenium, bottom section, indium, gallium, arsenium, and then between we have the tunneling layer, then we have 32.65%. So if we have multi-junction, here 3 junction, you can see it's very, very high. Okay, it's very, very good. When we have CIGS 18.6%, like that, you can see it's very, very good. And when we have multi-junction, again, I showed you only for multi-junction. So here you can have 38.8%, 37.9%, 32.8%, like that. It's very, very impressive. So that's why, but making problem with the multi-junction is you need very expensive equipment. Manufacturing equipment are very, very expensive. That's why cost is very high. Area is less. The manufacturing, and also you have manufacturing problem. Can you see it is 1 centimeter square, 4 centimeters square, 1 centimeter, like that. Okay, so this is the problem. It is very, very expensive. That's why we are still on the silicon-based solar cell. And these are the other materials. Here you can see when we have gallium, this again 39.5%. And here I want to show you the concentrator. Now this is with the concentrator. So this shows the intensity, 1x, 2x, this is 61x. At the lab, we do 1, but here this is 61. So we have concentrator. This is the type of concentrator here. You can see this is very small, 4J, 4 junction cell. And here we have lens, Fresnel lens. So all are coming, concentrating the sunlight into the our solar cell. So when we have like this condition, you can see efficiency is very, very high. When we have this condition, if the intensity is 665 times, then we have how much? 47.6%. So it is very, very expensive. As I told you, this is very impressive. But again, very, very impressive, but expensive. So you have to control. You have to then think how to manage. So this is the my thing, the concluding part. Now these are my collaborators, Professor Hyuri from Korea, Professor Idris Berja, who brought me in Korea, in Saudi Arabia, Professor Neil, his collaborator from the UA University, and I acknowledge the NPST as well as the UA University for the funding our research projects, and I'm grateful to the organizers, to the listeners, and thank you so much. And really, because of Mohan, especially Mohan actually, he told me, Gupta sir, can you present on the solar cell? So I tried my level best to give you about the glimpse on the silicon-based solar cells. And I learned actually. Thank you, Mohan, again and again.
वेलकम सर, आपको बहुत
really मोहन, मैं भी सीखा हूँ यार, बहुत सीखा हूँ मैं भी. I'm learning, frankly speaking, because see, we are not working on the silicon based solar cell, so we don't know much. But because of you, see, I made presentation file, just reading, learning why. So thank you so much.
We are learners, and I know मैं आपसे सीखा हूँ कैसे सीखना है. आप सीखते जा रहे हैं, मैं भी सीखते जा रहा हूँ साथ साथ में.
नहीं ऐसी मजा आता है.
तुरंत रिप्लाई किया मैंने, मैम को कहा कि भाई मैम प्लीज, गुप्ता सर इज रेडी. और शायद आप साइंस कॉलेज के एलुमनी भी है ना सर? आपने बीएससी वगैरह वहां से किया है साइंस कॉलेज रायपुर से? नहीं ना. अच्छा
नहीं,
थोड़ा सा ये कंफ्यूजन.
मैं वो राजनांदगांव से किया, दिग्विजय कॉलेज.
हाँ, दिग्विजय कॉलेज से. ठीक,
2 जगह से था एक्चुअली. बेमेतरा से 1 साल बेमेतरा में थे, दूसरे के ट्रांसफर हुआ नांदगांव में, सो नांदगांव मूव हुए. सो आई डिड फर्स्ट ईयर in Bemetara, previous final in Nandgaon, Digvijay College.
Sir, we have students from Digvijay College, Rajnandgaon also. So they are also
wow.
a great opportunity for them also. Question and answer. We have 2 students who want to ask some questions.
Yes.
Good afternoon, sir. And my question is it possible to make graphene-based solar cell?
Yes, why not? You can use graphene. Actually, people are using for the, instead of PT, you know, platinum is very expensive. So if we use graphene with the activated carbon, again, then we can increase the area of then we can increase the efficiency, as well as we can reduce the efficiency. We can reduce the cost. This is the advantages. And graphene we can use with the electrolyte also. So what will happen? Actually, see, our target is, of course, we are working on the electrolyte. When you are working for the batteries, for the supercapacitor, for the fuel cell, it should be pure ionic, no problem. Okay, it should be pure ionic. But for the solar cell, we don't bother about the ionic or electronic. If you have little electronic also, no problem. So this is the advantage. So we can use graphene in the electrolyte also.
Thank you, sir. Now
Most
next.
welcome.
Good afternoon, sir. And my question is, what do you think about the future of solar cell in India? Is it bright or not? As India is a developing country, so the cost of manufacturing solar cell is very high. So how to reduce it?
If you see the silicon-based solar cell, in India, we have so many, but unfortunately, all shut down. None is working. Why? Because we have solar plants, we have cheap material from the China. Okay. So if we manufacture silicon in the Govt, if we manufacture everything in India, then it will be cheap.
Yes.
It will be cheap. Okay. If you are relying only on China, you can't do anything. Okay. So made in India, it should be made in India from A to Z. All components of the material of the solar cells must be from India. Then only you can reduce. And you must have the technology also. So you have to work on the technology also. When I was in Korea, South Korea, we were working for developing the technologies from A to Z. We should not rely on other countries. This is the basic requirement. Is it clear?
So UAE में आप लोग मतलब किसी पे rely नहीं करते, खुद ही से पूरा A to Z.
आत्मनिर्भर बनना पड़ेगा. So we have to we have a big think station. We can think and we can work for this. So होता ये है कि हम छोटी-छोटी चीज जो है, चूंकि वहां से कम कास्ट मिलता है, तो ला करके फिर उसको यहाँ इंसेंबल कर लेते हैं और इंसेंबल करके काम चलाते हैं. उसके बाद फिर जब उसका मेंटेनेंस की बात आती है, देन गड़बड़ा जाता है, क्योंकि मेंटेनेंस जो है वो कर सकते हैं, टेक्नोलॉजी उनका है. अगर आपके पास सिस्टम है एंड यू कैन मेंटेन, then obviously the solar cell technology, and that this is India will have a bright future.
You can't believe while doing PhD, we were making furnaces, we were making our sample holders, so many things in our lab only. And I'm doing here in Saudi Arabia same. I did the same thing in Korea. Okay, what I learned during my PhD, I'm doing the same thing in Korea, in Ethiopia, even in USA also. I was doing, because my background is in such a way that I can make anything. I have now thin film homemade furnace, homemade oven. I have the sample holder. क्या बोलते हैं उसको, spin coater, homemade spin coater.
Yes.
Everything homemade. I can make myself everything. I don't bother. Otherwise, it's very expensive.
Thank you, sir.
Most welcome.
Thank you, sir, for your valuable talk on heterojunction solar cell system and perovskite material. That is definitely going to inspire our participant to work on it. Thank you, sir.
Most welcome. Thank you. Thank you so much to everybody.
Now it's time for next.
Now for next invited talk, I would like to invite Professor Mohan L. Verma. Yesterday, Rasmi Priya Topo introduced Professor Mohan L. Verma in the hands-on session. Let me add some new aspect about Professor Verma. Professor Verma did his master from Pandit Ravi Shankar Shukla University and did PhD from the same institute in solid state ionics. Professor Verma's research field of interest includes mathematical modeling, DFT based first principle studies, molecular mechanics and molecular dynamics simulation. 3 students completed their doctorate under his supervisions, and 5 others are working as for their doctorate degree. He has published more than 100 research papers in national and international journals. At present, he is working in collaborations with many national and international scientists. Professor Verma is core member of research group of one of eminent scientists, Professor Ravindra Pandey group. Apart from doing physics, Professor Verma is a good poet. You can read his poem from his web page. One of his poem is Shikayat. आप लोग वेब पेज उनका खोल के उसको जरूर पढ़ेंगे. Now I invite Professor Verma for his united attack, sir.
Professor Mohanlal Verma, sir, are you there? Maybe he has taken tea break, so let's take a 5 minutes break for tea break.
ओके नहीं मैं जस्ट कनेक्ट हो गया हूँ. तो थोड़ा फाइल डाउनलोड कर रहा था, ये ऑफ था करके मुझे पता नहीं चल रहा था. मैंने ओके जस्ट 1 मिनट में होता हूँ.
Now next session is start as sir has joined.
Excuse me, make little 5 minutes tea break, then everybody will be little relaxed. नहीं तो हल्की सी जलवा देते हैं नहीं. मोहन, you have already told 5 minutes break, so keep 5 minutes, then it is good.
Sir, actually the session actually delayed a bit, so we did, because hands-on session will be affected if we
okay. हाँ मोहन फिर चालू कर दो यार.
हाँ ठीक यस. Where is the Zoom? Okay, so let me share my screen. My screen is okay, visible to all, shared properly or not?
Yeah, excellent.
Okay, so thank you the organizer, especially that Awadhya ma'am, for giving me a chance to be the part of this wonderful international workshop. And this is both related to experimental and as well as simulation. So this is also in the hybrid mode. So I am also the hybrid person related to the simulation as well as experimental work. And the topic is related to that DFT exercise in the perspective of biosolar cell. So this topic is also hybrid one, because that solar cell experimental data well given by my senior, my sir, Gupta sir, and that was very well explained. And I am including some DFT based exercise on this biosolar cell. And in the yesterday, that the lecture given by Professor Pandey, that this bio term is now a very fascinating term nowadays, and one should go for this bio terms and biophysics, biomedical, medical physics like terms. So I am using this biosolar cell. So some DFT based studies I will include in my talk. So first of all, I'm very much thankful to my guide, Dr. Rakesh Chandra Agrawal, Dr. Ravi Pandey sir, and Dr. Rodrigo. Because of all these three, their blessings, I am here and able to talk in front of you all. And this also my team. I'm very much thankful to my team, that B.K. Shorao, Ajay, and Aarti, Nirbhay, Homendra Das. And these are my PhD students, and they did good work on mathematical modeling in experimental field too. And some DFT based students, that Rachana Singh, Upma, Swati, Harsha, and Tikam Soni, and many other students connected with me directly, indirectly, because I learned a lot from my students. So I am very much thankful to all this. This is my institution, Sri Shankaracharya Technical Campus. This is the lab, and this picture, the memorable picture. This is from in the year of 1900 and that 2013, when one international workshop was organized here, and Mr. Rodrigo was with us for a week. This is my lab. And the computational tool we are using, and that during hands-on training, Mr. Narendra and myself also give some glimpse on this installation of some tools, and in the application we will discuss today. So outline the ST functional theory at a glance, and what we are doing in my lab using this, and energy materials, batteries, solar cells, and obviously including that biosolar cells, some computer-based experiment, and how we start working with this system. So individually, as experimental, mathematical, and computational research, if they are doing individual work without helping each other, this the scheme will be like this. The result will be different, and the prediction of result that will be not comparable. So we have to work as a team, and there's as yesterday Mr. Rodrigo as well as Professor Pandey told us that we need to help experimentalists. We have to take the data from there and solve some problems they are facing, because they are binded with some physical conditions, and these computational tools we can have lots of flexibility. So this is that size and time reason we are working, and that it's a time this quantum mechanical we are using in the DFT with this picosecond time and in a nanometer regime, and we are a good predictor of some results. And this one good example that which gives the role of this DFT in predicting the properties, that is this topological insulator. These are the materials whose surface is metallic, but materials as a particular inner part is insulator. And first it is developed studied by DFT, and then experimentalists design these materials in the lab. So DFT was the details of DFT was given by Rodrigo. So I am not going to the details of this. So I would like to summarize this slide as just this is one interdisciplinary subject where we work with electrons. So we can also work with atoms, but in this DFT, this in the quantum mechanical level, we work with electron density, and this is a good tool for chemistry persons, biology persons, as well as different materials, metallurgy persons, as well as physics too. Obviously, material science is related to all these interdisciplinary subjects. If anyone wants to study this DFT, so I suggest these papers as well as review articles and books to start. That original, the original papers, and one should go through this initially to understand this DFT. Now, what we are doing in my lab using this system. Actually, I would like to say here this by showing all these slides. Just I want to show the capability of system. By using system, what we can do. So that materials are in the nanoregime. We are classified in the different dimensions, that 0 dimension, 1 dimensional, 2 dimensional, 3 dimensional materials. So we can, in my lab, we have tested all these materials. As Pandya sir told yesterday, that they have a periodicity of 7 years to change the field. But I think I have just 1 or 2 years to change the subject from one material to another material. It depends on that questions asked by my students, and their ways to associate with me with different materials. So this is that 0 dimensional material. This is the work of Sakshi, and this is bulk cage-like structures, nanoparticles, and that jet buckyballs, and its optical properties. And in the lab session, we will discuss how we will get these plots and absorption coefficient by using this is. So this is that 0 dimensional materials and nanoparticles. And then some more, the interaction of these 0 dimensional materials with the graphene, graphene planar structure. So the effect of this we have observed on the optical properties. So these materials can be used as magnetic nanoparticles, because we have observed by doping some atoms to these nanomaterials, and we have observed its magnetic properties. And yesterday we were discussing about Adya ma'am, that by creating data defects with this nanoparticles, this cage-like structure can be enhance that magnetic property, and we can try further. So these magnetic nanoparticles are very useful in especially to detect or cure cancer, especially that breast cancers. Though that's why we are interested to work further in this, and one of that student also associated with. These are some new buckyball type structures studying in my lab, and Renu is associated with this, and she is doing good, getting good result. And these are that total energy, optimization energy, that cohesive energy, and magnetic moment, and how we will get, we will discuss in lab session. That and today I think Narendra will discuss about this that formation energy or that cohesive energy, how to calculate. This is the projected density of state and density of state. In solid state physics, we think about that density of state. This is that number of states, available states per unit energy, per unit volume. And when we just project up to it, up to its orbital, then that is known as the projected density of state. And by using this projected density of state, what we say, we just tell the contribution of these different orbitals in conduction band and valence band, and the different devices, especially that property, it depends on HOMO-LUMO gap or that band gap. So we calculate this band gap by using this band plot as well as DAS plot, and the contribution of that orbitals in different bands, it is given by projected density of state. So again, in today's session, we will discuss how to plot and how to get this projected density data. So now move to one dimensional, and this is a beauty of this DFT. We can manipulate materials. We can study the materials, and so just we have taken one chain of this boron nitrate and that carbon chain. One can say that graphene chain, and that combination composite of this BN and this graphene, and we observed the effect of pressure, we observed the effect of stress as well as electric field on these one-dimensional materials. So that obviously that density of state plots are here, and that Fermi energy level it is being changed from one by the effect of that field. This is the charge density plot, and again this charge density means that a distribution of electrons around any particular species. It is given by this. So again, in the lab session, we will see how we can get. This is now the two-dimensional. Now we are just increasing in one-dimensional chain. We are increasing its direction from y-axis, so we can get that two-dimensional material that is known as nano ribbon, and that these are the nano ribbons at a different thickness, and its band plots are given in this paper. Now the planar structures nowadays, that thin film technology, it is boom. So in this, that counterpart or the second part of that, the theoretical, that is known as the planar structure. So we have designed this planar structure of TIN, HFN, ZRN type materials, and these materials are working as electrode materials for that photodiodes, photocells are used in retinal implant. So this is related to medical field, and we are also studying its nano ribbons, and this is in patent mode. So here just I am showing one published papers related to this, and again these are the PDAS and that bend plot, balance and conduction band of this. And then 2D stain is nanostructures, and this is related to electronic field, that is field effective transistor, and this is for the toxic gas sensors studied by Swati Verma, and she is from Electronics and Telecommunication Department. So I have told that this is one interdisciplinary field, so one can study this, and the effect of toxic gas and this nano ribbon, it is the change is observed in PDAS or IV curve. Yesterday, Pandey sir mentioned that I have to show this, so I am including this. So that this is nano ribbon, and by putting that particular gas, we can observe the change in its behavior as projected density epistate as well as IV curve. Now some more on this. This is wide doped SNS2 monolayer, and this is that interaction with this gas material. So these are a very good gas sensors, and one can observe the change in IV curve that when we put that gas molecules on that surface. So there is a change in charge density distribution as well as this IV curve. And for this IV curve, we use a transistor. That transport properties discussed yesterday by Rodrigo sir, and these are that density epistate in up spin and down spin. So we can include both spin of that electron given in different quantum numbers. Now these are the different gases emitted during that lung cancer. So for the sensor of this lung cancer, we can use these SNS2 materials, and we have studied this, and this is under publication. Now for the bulk materials, this silver iodide and the composite of silver iodide and copper iodide, and this is pure copper iodide. It's a movement from copper iodide to silver iodide, and silver iodide to copper iodide. So this is copper iodide, and we are replacing that copper elements, that silver elements with the copper elements, and observe that change in its optical property as well as electronic property especially. So there is a change in band gap and its optical property, and these are good optical materials. So this is three-dimensional material. Bulk type studies we can perform by using this system. Also another bulk materials, and again we have good optical properties of these Mn metal nitrides, that TIN, ZRN, and HFN. Now some biomaterial, that ketone is a very good electrolytic materials also. So we have studied its electronic properties by using transistor and resistor, and also observe the rotation of these molecules. Even one can use these molecules as a molecular switch. Nowadays, one nanomaterial in nanomaterial technology, electrical persons are just talking about that molecular switch. When we rotate the molecule and its behavior changes, and we have observed this theoretically by using this transistor band studies. So this is another molecules that is related to medical physics, and this is that materials related to the persons having some sugar problem. So that we have studied just a preliminary studies of that with homolumo studies, and that molecular testing, I think, yeah, this is molecular testing with ketone. Sorry, this is not that D-glucose for the diabetes people. I'm sorry. And again, we can study very chemical properties using this homolumo studies, and that HOMO and LOMO, these two terms are very familiar terms in the biomedical fields, biology persons as well as chemistry persons. Now the energy materials, we have this DFT batch studies of different materials, but to run all these devices, 0D, 2D, devices, we need some power sources. So the batteries, supercapacitors, and all other storage devices we need. So we have classified these non-renewable and renewable energy sources, out of which that solar cell was discussed in the last lecture. And, for these energy devices, we have studies in the battery materials in our lab, and all these, this is that new host developed by Professor Gupta, and we have studied it's theoretically its electronic properties and also the ionic properties by using these DFT studies. And again, we have some more electrode materials studies by Rachana, and this is that polymeric materials, the interaction of AGI with the polymer chain we can studies. And we have the change in its ionic behavior, one can observe this. Now another composite materials with PO, this with lithium chloride for the lithium ionic batteries, and this is one more PO with sodium iodide. And I think as a summary I can say that we can study that polymeric materials efficiently by using SISTA. Now solar cells, it has been widely discussed with by Gupta sir, so I'm not going to the details of this, what is that solar cell, what is the classification, but one thing I would like to show here, that is it's a theoretical based studies. So nowadays many commercial and non-commercial tools are available to study that behavior of solar cell, because in experimental that studying materials and designing solar cells and using some trial and error based that is costly, as I have mentioned in last session. So first we suggest that experimentally that you should design that solar cell by using this particular material. So for that we need simulation. So for simulation we have different simulation tools, and many commercial tools are available, but these are free of cost. As my motto is just we have to study that simulation free of cost. So this is one tool available in my lab, that is and for simulate this solar cell, what we need its configuration, obviously chemical composition, and we can study by using SISTA, its absorption coefficient and its optical properties, and its mobility of electrons and holes, band gap, and that effective mass, and all these effective mass, and all these can be studied theoretically. And you can go through my video channel to see how you can calculate all these parameters and put these parameters, and you can have this performance, whatever that parameter shown in the last lecture, one can calculate by using this simulation, by using this tool, that GP Videum. And these are parameters. So this is screenshot. So this is also, this is available free of cost, and window based tool, so anyone can use this. Now this bio solar cells. So in that biology term, that chlorophyll, we know that chlorophyll is a very good absorber of sunlight, because the technology of the solar cell, this depends on the absorption of sunlight at different angles, and especially that wavelength region, that visible range. And we know that plants are growing because of the absorption of that sunlight, and using that water and other things, and giving that glucose, oxygen, etc. So we know about that photosynthesis. So experimental people are thinking that when we extract that chlorophyll, and we mix this chlorophyll with some organic materials for the solar cells, or that silicon based materials, and perform that studies. But that limited studies have been started so far, and obviously there are so many limitations. So one can again studies all these by using DFT, what we have to do, we have to look at the chemical structure of that chlorophyll and study that interaction of the different optical materials already using in solar cells and try to enhance its stability as well as that performance of that solar cell. So this is that chlorophyll and that schematic diagram given, and that details have been discussed in the mechanism is same. Nothing based on that p-type and n-type materials will be there, and that will absorb that electron dollar electron acceptor will be there, and the working is same. Now the details of chlorophyll for DFT studies. So this chlorophyll, this is actually the combination of two parts. This part is that light absorber part at the center, this Mg2, and it is connected with nitrogen, and that is known as phytoporphyrines by biology persons, and this chemical person, and this is phytol tail. So the role in the solar cell or that absorption is in this part, and on the basis of the value of this R1, R2, R3, and R4 at a different composition, this chlorophyll can be classified into chlorophyll A, B, D, and F. And this is very least studied so far. And that A and B, especially that chlorophyll B, it is mostly available. By studied by experimental person. So what we are doing in my lab, we have designed this chlorophyll. We have taken that structure from internet and optimized the structure by using system. And these are different phases, X, Y, Z, different phases, and the structure is this. So this is the optimized structure of chlorophyll, and this is chlorophyll A. And we have studied this chlorophyll A, B, D, and F at the center. That is that MZ. So what I think, this is a good absorber, obviously, and just I will show that optical properties. But at the center, if I change that material in the place of MZ, what will be the effect? The simple questions, and just question must be there. So that MZ, okay, this is good material, and but if we replace this MZ with other materials, so I have taken randomly some atoms and replaced this MZ, then I have now this chlorophyll with its copper at the center, gallium. This is a very good materials related to optical properties. Zinc, this is also a good one. So this I have just replaced this MZ with its copper, gallium, and zinc, and observe its properties, that optical properties as well as that electronic properties, and I gauge this total energy, Fermi energy, the slightly change in Fermi energy, homolumo gap, that is and that cohesive and enthalpies. And what here we are observing that the behavior, that dust behavior is not much different of this A, B, D, and F, but its behavior is somewhat semiconducting, and that p-type and n-type semiconducting when we do this copper and zinc in place of this MZ. So this is a very good result, and I think this will change the optical behavior also. So let's see that optical properties. This is that absorption coefficient, and at this region, that is I should say this is the region where that it is absorbing that visible region. It is absorbing that light, and that I have just plotted that visible region also. So this blue color is related to F. Its absorption property is good at this visible region. So I can use this data and simulate the work by using that tool, and I can get results. So this is under study. I'm not going to the detail of this, and stability is also good. So now how we get all these results, what is DFT and how this, just I'm briefing this because almost two lectures have been given in this, what is that DFT and other things, and that CISTA also in the leap session we have discussed. So Obviously, that this is electronic structure based theory, and I would like to say that DFT is actually the progress in DFT is actually the conversion of that Schrodinger equation into quantum equation. That Schrodinger equation, when we think about that wave function, many body problem, and this quantum equation, we replace that wave function is the charge density, and that is a single one body problem. So there is a this actually took a lot of time to convert that Schrodinger equation to that quantum equation, and this is that journey. We have different Polyhedral models, Lorentz models in 1900, and obviously these models will have their own limitations, and then that Bloch's theorem that this is related to quantum theory, and then this that kinetic energy of this plot of energy K plot of these free electrons, as well as that localized electrons at different energy levels, that one particle inside that box in quantum physics we studied. So this is that band plot based on that. Now that a different approximation and discussed in details by Rodrigo sir. So these are different interaction between electron nucleus, and nucleus interaction, and that I'm not going to the details of this mathematics. So these are the terms. So in BO approximation, this is that nucleus, and these are that electrons. So the mass of this nucleus is very, very high, and so this is taken as stationary, and electrons are in motion, and it is calculated by this Bonham, and this is known as that Bonham, BO approximation, and then further modified by some other persons, that Hartree and Hartree approximation, and then this Hartree-Fock approximation, and every concept, that interaction of electrons and that replacement, the position, the changing of electrons, everything has been considered by this even that Pauli's exclusion principle. So lots of chemistry have been done in the development of this Schrodinger equation to quantum equation. So finally, we have now that quantum equation, and this is we use this quantum equation to calculate that electron density. So this is that flow chart discussed yesterday also, that we start from that initial case of charge density, then we calculate this exchange voltage, and then we solve this quantum equation and then get new density. And if this new density is as per our requirement, then it's okay. Otherwise, we just restart this calculation, and this is continue up to that particular level. So we use that LDA and ZGA. So the details of this LDA and ZGA we have discussed in the lab session. So these are that these are the DFT tools. So we are using that SISTA out of this, and these are that tools we have discussed yesterday in lab session. Now computer experiment is SISTA. So during lab session, we have this SISTA, the details of SISTA tools we have mentioned. So this is a well documented software, and why we are using SISTA, because it's computationally very cheap. So other software took very high computational time. So one can use the i3 laptop and start SISTA learning and using SISTA for the material research. So this is that format for input file. So in the last day we have discussed different components of this input file, and it is well documented. And if anyone wants to study this SISTA, so I recommend that you once restart from this channel, that SISTA India, and some tutorials on molecular modeling. And this is especially for the beginners, and I'm getting good response from all over the world. They are doing good. And in my lab, we have designed some scripts to make that study easy as well as interactive. So these are that script developed, and these are some tutorials also we have developed to run the SISTA. Okay, so sab electricity, water, and oxygen, these are very important components of the life. Thank you all, and thank you, listener, for your patience at lunch break at lunchtime. Thank you. Any question?
Myself, Vinay. Hello, good afternoon, sir. Myself.
Yes, good afternoon, Bolo.
Sir, I have one question. During transistor calculation, we have reasons such as scattering reason, buffer reason, electric reason. So, sir, it is specific reasons where we put electrode or scatter the material, or we can put in any direction.
Actually, that obviously SISTA is a good tool and it's flexible also. Even input file is flexible, but sometimes for the transport, especially, we have to fix a specific direction. That direction may be either x-axis, y-axis, or z-axis. So that transistor tool is designed so far. We are using so far along z direction, because that configuration of electrode materials and that active region, it's very important. What we take in transistor, we have two electrodes. One is that source, second is drain, and that active region by which that electrons have to transport. That region is active region, or that you are saying scattering region. So either one should take along y-axis or z-axis, but so far we can only have to align that device z-axis. Maybe if you want to study that transport along y-axis, then you have to rotate the material, not that electrode. You have to fix the electrode and rotate the materials. Remember this. So you can study that, yes, that materials is now along y-axis, because yesterday I think Professor Dr. Rodrigo shown that transport properties along y-axis and x-axis. So what they have done, they did that one material is designed, and we have obviously that one direction is flat, two direction, there will be two direction along z-axis and y-axis or x-axis. Then by rotating that transport properties have been studied. So far you have to use z-axis.
One more question, sir, I want to add it. If I have a number of electrodes, say I have 5 layers.
Yeah.
Of electrons is say suppose 30 electrons.
Yeah.
Of atoms. So sometimes when I go through the test files or some YouTube channels, I found that starting 3 lines, they calculate it is an electrode. They mentioned electrode, and last 2 lines they add up in scattering or materials section. It is possible to add number of electrons, number of atoms of electrodes in materials.
Idea behind this is to avoid the direct contact between two electrodes.
Yes, sir.
If you have an device and that two electrodes are being connected directly, then what will happen experimentally? Just you can think that positive bias and negative bias, they are connected together. There will be problem. So what we have, what in this transistor, what did we do? We take sufficient size of that active materials. Or if that is a simple molecule, if the size of that molecule is that, then we have to take some buffer layer. Buffer layer means that layer is not taking part in that calculation, but it is just avoiding to direct connection between that electrodes. So that's why that sometimes it is taken as 2 layer, 3 layer, sometimes 5 layer also. It's just to avoid the direct contact between these layers. Okay.
So thank you so much.
Yes, Gupta sir. Yes.
Very nice talk. Thank you so much. Lot of information.
Yes, sir. Thank you, sir.
Mohan, can we do one thing for electrolyte?
Yes.
See, for the solar cell, actually, we make redox couples.
Okay.
For the batteries, actually, we have say lithium iodide. So we have lithium plus iodide. But here in this case, we have 3 ions.
Okay, sir.
We have cobalt. For example, for the lithium iodide, for the iodide triiodide based system, we have iodide, I minus,
Yes, sir.
I3 minus triiodide, and we also have lithium or potassium or something like that, metal ion. Many times we have organic organic ions, cation. So is it possible
Yes,
to
sir.
add all three and then compute?
Yes, sir. What we will do, we just take that polymer or whatever that material first, and then we add that first atom, and then we optimize them. This actually that will keep up a proper position depending on that properties of that material. Then we add another material and then optimize, and then we add that third material and then we optimize. We can change the sequence also. We can check that if there is any effect by changing the sequence also. So A, B, C, if we have the material, then we will have that sequence A, B, C, then B, C, A, and C, B, A, R, N, A, that different combination, and check that, but it will take some time.
Mohan, actually, I am facing one problem.
Yes, sir.
Big problem, actually.
Yes, sir.
Major problem. See, iodide, triiodide, redox couples are very small.
Yes, sir.
Very small. But efficiency is less, 11.4% for disensitized solar cell.
Yeah.
Okay, this is the highest value. But when you go for the cobalt-based system or the copper-based system, you know, cobalt is big as compared to iodide. Triiodide is very, very big.
Yes.
But efficiency is very good. But this is for the liquid electrolyte. But when I used my material,
yes,
cobalt-based material, conductivity is very good. 7 into 10⁻⁻⁴ Simon per centimeter at room temperature.
Yes.
And when I go for the, I did anionic effect also. I used imides anion with the triplet ion. Okay. So conductivity is good naturally with the imide ion, TFSI, as compared to your triplet ion. But when I use for the solar cell, efficiency is very, very low.
What is the reason we have?
Kachra. उठा के फेंक दो उसको.
Actually, chemistry people are.
I'm working. I'm making cell. But efficiency is the worst. 0.2. Can you imagine? In iodide, triiodide, I was getting 2%, 3.7%. Okay, but in case of the cobalt-based redox-mediated solid electrolyte, of course, efficiency is less than 1%, not 1%, 0.5%.
We can. Yes. We can.
Why? This is question. Why? So this answer you should give me.
Yes. I can. We can, sir. किसी एक स्टूडेंट को लगा दूंगा और आपको मटेरियल लेकर के उस पे सिमुलेशन करते हैं. So because I have that software tools also, so theoretically we can check that its efficiency, how much efficiency or other parameters are being changed by whatever that configuration we are using, whatever that material we are using, and how it depends on that ionization as well as that size of that particles or that elements. We can check, sir.
I can say my project is failed. You know. My NPST project is failed. Why? Yeah, electrolyte is very good. Main target, okay, done. But the thing is the device. So why you are making? For device, naturally. Yes. Solar cell. Yes. If you don't have good solar cell, no use. So why you have this problem?
Yes, we can search.
I'm trying. See, the Hegfeld group, the Gretzel group, they have complete facility from Sweden, from your Switzerland. They have complete facility. They are reporting with liquid electrolyte. They are reporting 10%, 11%, 12%, 13%.
Excuse me, so we have a session.
Yes. So our time endless. So okay, sir, I will definitely assign this work to any student, and then we will search the answer of your question and your problem. Okay, sir.
Thank you,
sir, for giving your time. वहाँ कितने time है अभी?
अभी 11:25. Morning happy week.
यहाँ लोगों का
Lunch time.
lunch time हो गया. Okay, thank you sir.
Have a nice lunch. Have a nice day.
Okay, thank you. Thanks all. लंच करिए फिर हम लोग फिर लाइव सेशन पे मिलते हैं.
Okay. Thank you.
Thank you, sir. Thank you, sir, for your talk on density functional theory. That is definitely going to help us for our research. So thank you, sir. Thank you very much.
Okay, most welcome.
It would be okay to start hand-on session by 3 p.m.
I think we should start at 2:30. 30 minutes lunch break is okay. लोग अपना टिफिन कर लेंगे क्यों? नरेंद्र, are you there?
Yes, sir, I'm here.
I think we should start at 2:30.